do it. Hello, hello. I think we might be live on Facebook Live. Hello, hello. Welcome to the very first episode, but the second time of asking for Talking CFD Social. It's our very own brand new show, and you would have thought that three guys who spend their time doing reasonably tricksy computing stuff would manage to be able to talk to each other live on the internet, but it appears not. This has been a bit of a pain, but hopefully you guys won't know about any of that and you'll just enjoy the show. So as you can see, I've managed to rustle up a couple of co-hosts, so it won't just be me banging on. You might also see that I've got a bit jerky video. Again, don't worry about that. The other guys are much slicker, although Travis's picture is flickering around a bit. There he is. But we'll get back to them in a minute. I'll give you an idea of what this show's supposed to be first. It's supposed to be live, which is proving to be very, very difficult. It's supposed to have a theme. This one doesn't have a theme today. We're just going to introduce you to the concept and make you desperate to watch the next one. It's supposed to have some input from you guys. Hopefully, Facebook Live is going to be a good place for that. We shall see. You should be able to comment and what have you and get involved. Maybe even come on if we can figure out how to do that. It's supposed to be lighthearted. Hopefully this one will be lighthearted. Like I say, we've done this a couple of times now, so it's probably getting a bit tiring. And lastly, following in the footsteps of the podcast, it's not supposed to be a super technical show. Might get a little bit more techie than the podcast, but we shall see. I had a thought that it might be a little bit like the old Top Gear, where we've got three guys. You know the bit where they sit on the sofas and they sit around and they're talking about stuff. It's going to be like that, but with less money, less people watching, and less cars, but more CFD. So probably how the BBC really intended Top Gear to be before it got corrupted a little bit. So, as I said, three of us. Who wants to introduce himself? Who wants to be May or Hammond or Clarkson?
Go on, I'll jump in.
Go on then.
Hi everyone. So I'm Simon. As you probably guessed, I do a bit of CFD. I've done so for quite a while. At the moment, I work for the Manor Formula One team, doing CFD on the F1 car, which is obviously pretty challenging, pretty fun. A good challenge in terms of CFD from external aerodynamics. Obviously, getting involved in some of the efficiency sides, process development. So, kind of bringing all those things together. So I've been doing that for a while. Prior to that, I spent a bit of time out in industry, trying to make things and simulating how things work. So quite a lot of that was physics development stuff in OpenFOAM. I think Robin will probably touch on the fact that there's a bit of a OpenFOAM, open source trend amongst us guys. So quite a bit of experience doing that. Saw some quite cool specific OpenFOAM developments, not done by me. I had a very bright Dutch guy working for me who did some very clever fluid structure interaction with some funky piezoelectric materials and compressible multi-phase flows. So if we want to get into the techie stuff, I can tell you all a little bit about that. Prior to that, did a bunch of consulting work, and then back in a time that I can't remember, I did one of those PhD things.
Oh dear, yeah. It's too long ago. We don't talk about that. Cool. So that's Simon. How about you, Travis?
All right. Thanks, Robin. So I'm Travis, and I work for a small software company out of Fort Worth, Texas, on the sales and marketing team. The company is called Pointwise, and we develop CFD grid generation software. And before I get into talking about what I do here, kind of my CFD background began in graduate school or the end of undergraduate when I was actually interning here. And then in graduate school, getting my master's degree, my focus was on design optimization, and in particular, evolutionary algorithms, and using them to design things like a vertical axis wind turbine or something like that. That ended up actually being my thesis. And in doing so, coupling that system with CFD and on the meshing side as well, automating the entire process. It was really interesting. Did a little bit in GPU computing as well for finite element analysis, kind of accelerating those algorithms using the latest GPU hardware at the time, back in 2010, 2011. Obviously, things have come a long way since then. And now I'm here at Pointwise. I started full-time here back in 2011 after getting my master's degree. Like I said, I'm on the sales and marketing team, and my primary role here is new sales. And so what I do with new sales is work with prospective customers or current clients wanting to add capability, take control over their meshing, more control over the mesh to improve accuracy or solution convergence, work on more complex applications and that kind of thing. And so that's a very technical process because I work with the end users, the actual engineers, quite a bit to develop a plan for an evaluation and a set of requirements that we need to meet. And through that evaluation, we basically determine if Pointwise is the right fit for their organization. And kind of the other side of that is on the sales and marketing team, I do a lot of technical marketing activities as well as other people here in the company. That means, I'm doing things like social media marketing, Twitter, Facebook. I'm publishing a lot of stuff to YouTube videos on how to use our software, best practices for grid generation for CFD, writing technical papers for conferences, which are heavily application oriented. And that's kind of where the running of the flow solver comes in. We're heavily a pre-processing company generating grids and best practices for making meshes, and rely a lot on our clients to provide feedback. But occasionally when we embark on one of these studies and we're doing something application based, we end up running a calculation ourselves to validate a particular meshing strategy or topology. And so I do a lot of that when preparing papers like that for conferences. I put on the webinars. If you haven't seen our webinars, you should definitely check them out. So I put on those webinars with either a joint customer or a partner, a software partner. And those are typically very technical and showcase, again, best practices in mesh generation and often the entire CFD process. And that's kind of my background and my experience. It's heavily on the pre-processing side, on the meshing side of the CFD equation. And so obviously that's kind of what I can bring to the table.
Cool. The stream's a bit broken up for me, but Simon says not, so we'll keep on, see how it goes. I am when I'm not doing the podcast, which you might have heard of soon as you're here, then I do some aero consultancy. And mainly low speed stuff. So mainly what you might call simple CFD stuff. So it's mainly for companies that make things, in particular companies that make stuff that move along the ground, race cars, road bikes, buses, trucks, trailers, normal cars, that sort of thing. Occasionally things that go on the water, even less occasionally things that fly, drones and that sort of thing, but mainly ground vehicles. So most of the stuff I do is low speed, as I say, pretty simple physics, but reasonably complex geometry. That's where I kind of come in, and always some very complex constraints, things that are tricky to make, tricky to operate, or that might be rules and regulations. So you get a lot of that, particularly in competition and race car and sport stuff. So rules that are there for seemingly no other reason than to be rules. Or usually some combination of all of those things. I've been doing that kind of thing for a while. I'm doing it myself for the last 4 and a bit years. So like I say, if I'm not doing the aero consulting, then if I am working, because I like to spend plenty of time not doing that, then I'm probably doing something related to the podcast, which you can check out at talkingcfd.com if you haven't already. So there weren't any kind of podcasts in the sort of CFD space when I started, and I like listening to podcasts, and there weren't any CFD related ones at the time. And I thought, well, there's 2 reasons for that. Either it's because nobody wants to listen to them, or just nobody's doing one yet. So I thought, well, let's do a podcast, see what happens. see if anybody listens. If they do listen, we get a bit of decent feedback, then we'll do some more. So at the start of the year, did a dozen interviews of various flavors with various different people. Haven't had either of these two good guys on there yet, but this time. And as I say, the response was quite good. So we are just starting up the second season. I think we're 3 episodes in or so, something along those lines. I record them all in advance, so I'm not quite sure how far in we are. And this is the kind of companion stroke sister show to that. So this is Talking CFD Social. And that is the kind of full circle, I guess. So that's who we are. You've got an idea what we're going to talk about in terms of future episodes. They're going to usually have a CFD theme. So we've bounced around a couple of ideas about what we're going to talk about, but we are open to ideas. So if you've got any ideas, then chuck them in. If not, then what we'll do is probably publicize what we're going to talk about for the next episode. And if it's something you think you're going to be interested in, or you've got a particular opinion on something, then you should be able to join in the comments and interact and things like that. Give us some feedback, nice feedback. We don't accept bad feedback. Interact, join in. The podcast is very, as I say, they're all recorded in advance, so there is no opportunity for a listener to interact really. This is not the case. This is live, and if you've got something to say, and you particularly if you know more about it than we do, then we want to hear you on here and hear what we got to say. We're learning about this stuff as well. We're going to bounce some ideas about and learn off each other, but we particularly want to learn off you guys as well. What was next, guys?
Most interesting application.
Okay. Wow. So I think before we do that, Simon did mention, and I should have brought it back round to it, that my kind of CFD comfy place is OpenFOAM and PowerView. So I do my pre-processing, solving in OpenFOAM, usually remotely in the cloud somewhere, hiding away, and then do the processing in batch, typically in PowerView, but also interactively in PowerView when necessary. You'd think that for somebody who spends his working life doing CFD in the cloud, then hooking up to some live stream wouldn't really be that difficult, but it has proven to be so. Simon also mentioned that he's a bit of an open FOMO. Is that right, Simon?
Yeah, absolutely. I mean, I started using it quite a while back, a few jobs ago, but I think it was still a little, certainly not as mature as it is now. The capability was there, the stability probably wasn't, and it was only in previous jobs where if you found the right type of person who was really quite good at fluid mechanics, knew a bit of computational fluid dynamics, was kind of intrinsically comfortable sat in front of C++ code to kind of bring some of the kind of capability and power to fruition. You don't find many of those people. Certainly, I've not met many of them. A particularly rare breed. So that was kind of a bit of a not really an epiphany, but a kind of a notable moment for me where you could really kind of see the power and the use of the approach. And certainly from my side, it's a tool that's really useful in terms of being able to address all the sorts of things that you need to if you're trying to do CFD in the motorsport, Formula One applications. You need as much control to be able to make it go efficiently, accurately, spit out the particular numbers you're interested in, add some bits that you want to add that the aerodynamicists are after. So it kind of opens all that up to you. It does let you know who's boss every now and again, which is usually the computer and usually the C++ code and not you. But it's I guess you guys have hopefully you'd back me up on that. When it's not working, it's your fault.
Absolutely. So you would you say you were a bit of a developer or just a user?
Well, I'd say I sit squarely on the fence in between those two.
Really?
I like a little bit of C++. I couldn't explain to you the architecture of OpenFOAM from a C++ perspective, and the polymorphism and all the those funky development terminology. But in terms of having a look at the code, understanding what it's doing, making some changes as you see fit, then I quite enjoy that. Obviously, it doesn't go too deep. So, you know, it could be boundary conditions, it could be turbulence models, could be wall functions. It's certainly not matrix equations or any of the deeper structures, but I do like a little bit of coding. I don't like to do coding all the time. I like to try and do a bit of engineering as well. But I did do a bit of C coding back in the dim and distant PhD days, and that's kind of stuck with me. Which is kind of I was quite fortunate that when I did my PhD, my supervisor was quite positive about actually doing some code development myself. So I quite liked getting into it and understanding what was going on. So I did write my own C solver 15, 20 years ago now. And that's kind of stuck with me. But even in the intermediate term, kind of using commercial software, so Fluent, I found that was quite a useful thing to have done. So I have a bit of a grasp of what's going on behind the scenes. So I've always kind of liked that extra element that that you can get if you're prepared to look in a little bit closer.
Yeah, cool. If I remember rightly, you were at Imperial, weren't you? I mean, that's a hotbed of writing your own CFD code in there, isn't it?
Yeah. So I think I was there from, oh dear, I can't even remember the dates these days. 2000 to 2004, and I think 2004 was when they turned foam into OpenFOAM. So I was kind of around there when foam was around. Some of my friends who were doing PhDs were using foam for their applications, but it wasn't. There was quite a lot of different. It was typical academia in the sense that there was different groups doing different things in different ways with different tools. So it wasn't a case of everybody in the mechanical engineering department was using foam. Some of the guys were. Some of the guys were doing other stuff. I was doing some other stuff which involved me writing things from scratch, which was painful, but fun as well.
I bet everybody had their own special flavour of the code anyway.
Yeah, I mean, it's the classic case, isn't it? You come in to do some research and then you spend the first bit figuring out what the person who wrote the last version of the code that you're starting with was trying to do with it. But then it's a different kind of fun when you're trying to work out how to write a particular type of Navier-Stokes solver and you've just got a blank piece of paper in front of you. That's also kind of fun as well.
How about you, Travis? Do you get to spend much time on the solving side, or are you firmly pre-processing?
A little bit of both. More on the pre-processing side, since that's where I spend most of my time, is generating grids and coming up with best practices. Like I mentioned before, if we're not running calculations, we're definitely getting feedback from our customers, our clients, people using the code, telling us what's working, what's not. It helps influence, future decisions, new features, that sort of thing. But occasionally, as far as on the technical marketing side, when I'm writing a paper or I'm putting together a webinar and it's really application focused, we do run calculations, and I've been using OpenFOAM since I think 2010 is when OpenFOAM was introduced to me. And it was really interesting because up until that point in graduate school, my master's, I was using all commercial software for the solving side of things. So I think it was interesting to me because it was all command line driven. There was no UI. I really enjoyed scripting, getting tools like Pointwise to build meshes for me automatically through the scripting language, using Bash to tie together a bunch of little utilities and that sort of thing. So it was an environment that I was really comfortable in, and so really drawn to using OpenFOAM. Obviously, at the time, I was using Pointwise to even build my meshes then. And so, yeah, like I said, I mean, when it's application oriented and I want to validate a particular strategy or topology or something like that I'm working on, either for a client or for a paper or something like that, I'll resort to using OpenFOAM for some low speed external aerodynamics. That's primarily what I'll use it for. Simple foam, maybe pimple foam, maybe some dynamic mesh stuff. I've done some like vertical axis wind turbine or hydrokinetic turbine simulations in OpenFOAM, but primarily like CFD around, vehicles, automotive applications, aircraft, that sort of thing. I've dabbled a little bit into SU2 out of Stanford University for some of the higher speed external aerodynamics. My colleague uses Fun3D quite a bit for some external aerodynamics as well. And so there's a number of codes that we do use to, again, validate particular strategies or help put together a paper or a piece of content that we intend to showcase. More recently, I've been using Caelus, which is kind of a derivative or fork of OpenFOAM by Applied CCM. And so, but again, it's an environment that I'm really familiar with, this OpenFOAM environment, hopping in on the command line and being able to run these utilities. Also running on a Windows machine, so I've got a Linux box downstairs in the server room. But one of the nice things about using Caelus was that I could load it up on my Windows machine. Again, I'm presented with a terminal. I can get in there and start using it right away. So that's how I use CFD. I would say split maybe 90 to 95% of my work is on the pre-processing side, on the meshing side, just building meshes. And documenting that process and sharing that process, whereas maybe 5%, 10% is actually running calculations and putting together some of this content.
Yeah. So, I mean, it sounds like if in the event that we have an episode talking about solvers and things like that, or even open source or commercial, we might be a little bit light on recent commercial code experience, so that might be a good opportunity for somebody to jump in and set us straight on what's going on these days. So Travis reminded me, greatest ever CFD experience or triumph, or the one you're going to get a knighthood for. What is it? Go on,
all right,
Simon,
I'll take it.
Tell us. Oh, Travis has got it.
I'll talk about it first. That's fine. You all have already heard it. All right. So my kind of greatest triumph in the I'll expand this to CAE space because it's on the finite element side, but has kind of migrated to the CFD side recently. That is, and again, I feel like I just told you guys this because this was yesterday. But anyway,
all those listeners, Travis, nobody else saw that.
Nobody else saw that. That's right. The secret. So yeah, we were approached by a client who was building meshes for centrifugal impellers, and they had automated the entire process for that. So they would bring in a geometry. It automatically create a hex mesh for these geometries. And what they wanted to do is they were running these structural analyses on these impellers, and they wanted to predict these higher frequency failures. And to do so accurately, they need to throw a ton of points at it. So in FEA terms, that's H refinement. They're just throwing more cells at the problem, which isn't always the most efficient approach, particularly on the FEA side. And so one of the other ways that you can do that, improve accuracy, is through P refinement, where you're elevating the order of the basis function, the polynomial basis function for the assumed solution per element, and you're doing a little bit more work on the element side. And the requirement for that is you need more nodes per cell. And for a typical linear mesh, the edges have straight sides. You've got a node at either end of an edge. With these types of meshes, you have nodes on the interior of edges, which basically allow these elements to curve, and they're often referred to as curvilinear elements. And so this is kind of what the client wanted. They wanted to elevate the order of their hexes to quadratic, or P2 meshes, second order. And to do that, we needed to take the linear meshes that we create, because we're primarily in the CFD space. For second order simulations, these elements are linear. They've got straight edges. And we needed to find a way to insert these nodes, but not only just insert the nodes, because that's actually pretty straightforward. It's projecting these inserted nodes onto the geometry where appropriate. And so that's kind of where I got involved. It was a really interesting project. I think it was back in 2011 that I started working on it, just after I started full time. And I was kind of in a position where I could invest quite a bit of time in this project. And so a colleague of mine in the development team put together a nice little library for me to call and access to get all of the grid information that I would need for the linear meshes that they had generated. And then I would basically compute the locations of the new nodes, place them where appropriate, determine if they need to go on the geometry and use some of our tools for doing that, and then project them onto the geometry and then update the element connectivity. So in the end, we we would export a file that had the higher order connectivity for the elements that our client, could then use and run these calculations. And it was interesting. We ended up writing a paper for 2014 Turbo Expo on this, and it did improve the accuracy. We could use fewer elements to do this. We're curving elements, so it takes fewer elements to actually represent that geometry. And the interesting thing was, I'm not a developer. I learned a lot in the process. I used TickleTK. Our glyph scripting language is based on TickleTK, which was a language I wasn't that familiar with at the time either. And so I learned quite a bit in the process. But not only that, just higher order element mesh generation in general was kind of getting started, and elevating the order of elements was one of the approaches to take to generate these types of elements. So it was a really unique application, and it was one that I was excited to work on because we saw it through to the end. We actually got to see the results of elevating the order of these elements for this client's application. Nowadays, and that was on the FEA side, where things are a little bit easier because the elements tend to be more isotropic. And on the CFD side, which is what we're working on now, obviously this has become a lot more sophisticated since it was kind of prototyped in our scripting language. We've invested quite a bit of effort in working on higher order CFD mesh generation, where you have to take into account the fact that your elements in the boundary layer region are highly anisotropic, really small. And so when you insert nodes and you project them onto the geometry, because you're using fewer of them to actually represent that geometry, you can actually invert an element. And so you have to have a way to propagate that deformation into the interior of the mesh. And that's something that we've been working on. And we've written a paper about it. And there's an article on our website about some of the efforts in this area. But it's an interesting space. Higher order CFD solvers, there's not many of them at this point. And so the mesh generation side, the meshes are starting to become more required, so that you could actually run these types of calculations and develop these types of solvers. So that was a really interesting project. Again, kind of more on the FEA side, but has transitioned to the CFD side over time.
See, now you've given the game away that we were talking about this sort of thing yesterday, that there's a bit of a theme there between your story and the one that Simon was, hopefully the one Simon's going to tell, unless he's changed his mind from yesterday, in seeing something through from kind of an idea to almost through to fruition. So that also runs into some of my stuff as well. But Simon, do you want to go?
Yeah, okay. So I guess not so much as a pure CFD triumph, although the end result was really quite pleasing, which I'll come on to. But for me, it's more about kind of being involved in the whole process of designing something and seeing how it performs, and seeing the CFD follow on to all the other parts. So the thing I'll talk about is back in, when would have this been? This would have been about 2009, 2010, around that time. I think it was, it was even earlier. So it would have been 2005, 2006, 10 years ago. So I was working in a consultancy group at the time, which was where Robin and I first met, a little group called Advantage CFD that used to be part of the BAR Honda Formula One team. And they did CFD for the BAR Honda Formula One car, and they also did external consultancy. That's the part I was involved in. And I was doing some external consultancy work trying to reduce the drag on the track cyclists for the British Olympic cycling team, to try and make them go faster for the amount of power that they were able to output. So we did some interesting CFD. It was quite a tricky CFD problem. So the Reynolds number of flow over these bikes at the speedway cycle is very much in the transitional regime. So it's the tricky bit between laminar, turbulent, or sitting on the fence and trying to work those things out. So from a CFD point of view, it was nice and challenging.
Couldn't have been in a worse spot.
Well, you can't really say, well, can you make the bike quite a bit bigger so that the length scale changes? No, you can't do that. So we were doing some CFD work with athletes that were scanned. So we got athletes to sit on bikes and sit still for a while somebody laser scanned them to get the input geometry into the CFD process.
I'd never seen that before, by the way. That was the first time I'd ever seen a project that did that.
Yeah, absolutely. Same for me. And it was a little bit weird when you were doing the pre-processing.
Oh yeah.
You were looking at a real person sat on a bike. Um, which, you got used to it after a while, but it was definitely weird to start with.
Well,
And
especially
then
when you met that person later.
yeah, and I was just spent 2 days turning you into triangles. So yeah, that was fun. So doing the CFD was obviously an enjoyable thing. Trying to work out which bits of bike geometry to move to try and reduce the drag. Some quite complicated airflows. Obviously, different athletes have different body shapes, sizes, so there was some kind of geometric variability in there. So from a CFD point of view, that was interesting and rewarding. But the main part I was trying to get to was, having done that, was then the opportunity to go and see how some of the parts that we modified and designed in CFD actually performed in the wind tunnel. So it was down at I think it was the RJ Mitchell wind tunnel in Southampton. We went down there with some of the athletes, so they had a nice setup there where you had some camera feeds of position being shown live to the athlete on the bike, and then a readout of their drag, so they could kind of get an understanding of how much they could save in their drag by moving their body around as they cycled, which was kind of separate from the CFD, but really interesting to see from a kind of athlete performance perspective, because then they'd be moving into all these kind of funny shapes. And the guys in the control room will be going, "Wow, Bradley, you've knocked 10% off your drag," but then he'd be cycling along like that. He couldn't really go very far in that position. So it was kind of useful to give. It was really valuable to give the athletes that perspective. But we were doing a lot of work in the background, trying to reduce the drag and to give them a real handle on how difficult it is to give them a drag reduction that's sustainable over how many laps they might do of a velodrome. So from an engineering perspective, really nice to see that level of feedback from the wind tunnel, but then to take it on to the next step as well, which was to go up to the track in the velodrome in Manchester, and to see how those things performed in terms of how fast athletes could go around the track for a given power output. And we saw that all join up. So we made some developments in CFD, saw them give gains in the wind tunnel, and then saw them go up to the velodrome and give some gains there. So that was really nice to see that kind of go full circle and see the thing that you've been working on pass the first test, pass the second test, and actually then go and make it out onto the bikes that went out to Beijing, which I did actually just have a quick Google of to see how many medals they won, and I couldn't count all the items. So it did quite well in terms of actually making the cyclists win some medals. But if you, one story I will quickly say, if you ever find yourself down in the RJ Mitchell wind tunnel in Southampton, go and have a look at the grating. So at the end of the working section, there's a kind of grating section to make sure things don't fly around the corner and end up in the fans. The last time I saw it, and there was a video that I think either UK Sport or British Cycling did a while ago. So it's on social media, and out there you can see it's kind of got a little bit of a pink tinge to it, this grating. And that was partially my fault. So when we were validating the CFD model, we were looking at surface flow over the legs of Jason Queally. So Jason Queally was one of the guys that I turned into triangles. And obviously, as part of the CFD, one output you can get is some kind of oil flow surface wall shear output to have a look to see how the flow is going over different parts of the body. So we had that kind of picture from CFD. And we managed to convince Jason Queally to get into a very tight, uncomfortable black cat suit thing, and then sit on the bike in exactly the same position he'd sat on the bike to be scanned in. So he was probably a bit fed up of that. And then we managed to pour pink Floviz paint all over him, stand back and watch what shape it took. And obviously some of it came off and went down the tunnel onto the protective grid. So if you ever go down there and you see pink paint on the RJ Mitchell wind tunnel protective mesh, it's a little bit my fault and Jason's fault. But the satisfying thing was that the Floviz showed good separation agreement on his leg to my CFD model of his leg. So that was another nice thing as well.
So that's your CFD triumph.
Yeah, and some other stuff about Floviz paint and triangles and things. Yeah,
cool. I spent a bit of time in wind tunnels doing my PhD, and if you ever went near anything with Floviz paint, you were immediately chased off by couple of texts or something like that. Or if they didn't manage to chase you off, then you had hours and hours and hours to clean it up.
Yeah, I think we got away with it quite lightly, to be honest. Yeah.
Yeah, somebody else probably didn't, though, did they? There's probably somebody who spent hours. And I thought you were going to say originally that you need to go down and check, and there's probably a gold medal down there or something. There were so many of them that one ended up down there. So I told a slightly different story yesterday, and it was not of a CFD triumph. It was of a particularly tricky project that I'd done. So I will tell the same story just for continuity, in case the previous story ever leaks out somehow. So I have done many projects on fairly complicated car geometries. So I don't know if Simon ever got to do any when he was at Honda, but if he spent any time doing the wheel internal models, you know that there's a bit of mesh in there, and the various other bits of the car that we used to spend a very long time making meshes with. I will say that we didn't have Pointwise, so if we did, maybe we would have saved a bit of time there, and putting together touring car models from body in white, things that have got gaps that you wouldn't believe, and those sort of models, although it takes a while to get them out, they are quite satisfying. But this particular story revolves around CFD of a fence. So I was approached to do a CFD study on the kind of fence that they put up around building sites to stop people getting clobbered by bricks and things like that. Usually they just put up a big wooden board, put two posts into some concrete, and they're finished. In cities, it's not always easy to be digging the holes to put the posts in concrete, because there's services under the ground and things like that. So this particular company that I was working for, they have effectively a giant concrete block that they put the post in, and then they slot a board in, and there's your hoarding. However, in order to get that past the powers that be at a given building site, you have to show pretty well that this thing's not going to blow away. Now, we knew it wasn't going to blow away. They knew it wasn't going to blow away, but they also had a little Excel spreadsheet type code that told them it wasn't going to blow away. But we wanted to look at it a little bit more than that, and if possible, make some modifications to it so that it had an even bigger safety margin, or it performed in even higher wind conditions and things like that. And the scales involved in this thing were just enormous, from a board being like 5 mil thick to one that was, I think the thing is 3 meters tall or something like that, and all down to the little details and things. And a run is kind of like 50 meters long by just nonsense. And then trying to validate that against both the code that said it wasn't going to blow over, and then sort of real world observations when most of the interactions involved things bending and giving and flexing a little bit and this, that and the other. It was a challenge. So as I said yesterday, if anybody comes to you saying, I've got a little project for you, why don't you just blow some wind over this fence, run a mile. It's don't do it. Don't do it. It's not good on any. Give me an engine bay or something like that any day. So that's my little story of that's where this bit came from.
Interesting, Robin. You mentioned the wheel internals, which seemed pretty much the inauguration into surface geometry tidy up and meshing. Certainly in that little group that we were working in, and it's one that I've used with other folk. After that, it's quite a good training exercise to give them.
Oh, it still lives on, does it?
Well, not at Manor at the moment. In the middle of some work involved with sports cars in America, and so I took a couple of guys on while I was doing that, and it was always a case of, okay, the preprocessor we were using at the time was the same one, so it was Answer from Beta CAE, and it was the first couple of weeks, right, here's probably the least tidy, probably one of the most geometrically complex bits of geometry with loads of nuts and bolts that you really don't need. Here's Answer that you've never used before. Please just tidy it up. I remember when I did it, it took me, I think I was sat in front of it for about 2 weeks. But once you come out the other side, you kind of knew your stuff. So that.
But wasn't about like 3 or 4 days of that 2 weeks just finding where the button was?
Oh, well, or just, I think the first half a day was just like, wow, that's a lot of buttons. Oh, here's another deck. That's the same amount of buttons on this other deck. Okay. So the question that just popped up in my mind was, you and I obviously shared a similar kind of meshing inauguration. Travis, I was interested, given your, obviously with Pointwise and making this and selling this and supporting this type of software, what was your kind of meshing inauguration?
I would say, let's see. Well, when I started working here as an intern in 2008, I was on the technical support team. And so my inauguration was using our legacy product GridGen and working through the tutorials. But beyond that, I had a mentor here who would throw applications my way, people who were evaluating the code, who were thinking of evaluating the code or just challenging meshing applications, anything from a full aircraft to an automotive application before our geometry clamp tools were as mature as they are now, things like that. So just a lot of different things. Again, we work in a lot of industries. And so I think the more interesting thing for me was it wasn't just one project that I did. It was a whole host of projects across pretty much any industry that you could think of in a very short period of time, and kind of tackling all these using different topologies, different meshing strategies, that sort of thing. And then on my graduate research, which was more on the 2D airfoil vertical axis wind turbine side, so a little bit simpler. But now when we get interns here, I have a library of these really complicated geometries that not only I worked through when I was starting here, but that I've kind of accrued over the years. And that's the first thing that I give people is, all right, this is the best way to learn is start tackling. This is the end result. Let's see how you get there, and let's talk about it along the way. And I think that's kind of when I was doing this, when I was being mentored and that sort of thing, that was the approach that he took was, here's a really complex automotive application, or here's a full aircraft, right? In high lift configuration, this is the Y plus I want you to target, or more like, this is the flight regime, figure everything out. And when I couldn't figure everything out, it would spark a discussion and we would talk about it. And I would learn a lot from those discussions. And in the end, I would have a mesh that I was really proud of, that he was proud of, that met the requirements, and kind of took that and applied it to each of the other problems. And so I kind of try to do the same thing when people are learning our software for the first time, or we're getting interns who are using it for the first time in a kind of a production level environment.
I find it quite funny that you can have a mesh that you'd be proud of, and I know exactly what you mean because I've had hundreds of them. But it just to an outsider that would be a very strange concept, I think.
Yeah.
So I think if anybody is watching this, that they've probably got the idea of where we're going with this this Talking CFD social, and we're going to be back for more. This was just to give you a bit of an idea of where we're planning to go with it. So if it is something that you're interested in, then I guess some sort of like, is that a like? That's a like, isn't it? On Facebook of the Talking CFD page should get you some sort of notification when we go live next time, if we manage to put that together, seeing as it was hard enough to get to this point. What have I missed?
No, that was it, I think.
Yeah.
Awesome. Yeah. Right. So we will wrap this up, I guess, then, and put it out there and see what everybody reckons. If you do like it, leave a comment. As I say, we only do nice comments. The other ones will be deleted. So thanks, guys, and see you all again soon.
Great stuff.
Thanks, Robin.